Algebra 2, Section 7A, Graphing Radical Functions. In today's lesson, we're going to learn how to graph radical functions. Okay, so let's look at this. A horizontal line can intersect the graph of f of x equals x squared twice. So we know a vertical line will intersect its inverse twice. So its inverse, because of the vertical line test, is not a function. But we can rewrite the domain and range to make it a function. So we could say, hey, in the domain of f, x has got to be greater than or equal to 0. When we do that, the range of the inverse becomes y must be greater than or equal to 0. Therefore, x would also have to be greater than or equal to 0. Okay, once we put that restriction, and once we put that in the domain, the inverse is now a function because the vertical line test only passes through one line. So the inverse of g of x equals x cubed is a function. Let's look at it. When you plot x cubed, you're going to get a little S-shaped curve. So none of the points cross through the vertical line. Its inverse is also a function. A radical equation defines a radical function. The graph of a radical function like this, y equals the square root of x plus k, is nothing more than a translation of the graph y equals square root of x. If k is positive, the graph is translated up k units. If k is negative, the graph is translated down k units. Translating square root functions vertically. So graph the square root of x plus 2 and square root of x minus 1. The graph of the y, square root of x plus 2, is the graph of the square root of x shifted up 2 units. Okay, shifted up 2 units. The graph of the square root of x minus 1 is the graph of square root of x shifted down 1 unit. The domains of both functions are set of the non-negative numbers, but their range may differ. So the domain for both would be x greater than or equal to 0. The range, however, varies. All right, the range for the square root of x plus 2 would be y is greater than or equal to 2. The range of the square root of x minus 1 is y would be greater than or equal to negative 1. So graph the square root of x minus 3 and the square root of x plus 3. Well, we know these are just going to be translations. So the square root of x minus 3, we know we're going to start at negative 3. So there's 0, negative 3. So when x equals 1, y is negative 2. When x equals 4, y would equal negative 1. And when x equals 9, y would equal 0. So here's our graph. Nice and easy. So now let's do y square root of x plus 3. Well, when x is 0, y is 3. So it's going to match the exact same coordinates, the exact same arc, but it's just going to be translated up 3 units. Okay? Easy enough. So the graph of y equals the square root of x minus h, where h is inside the radicand, is a translation of y equals square root of x, just like we've done before. H is positive, the graph is translated units to the right. And if h is negative, it's translated h units to the left. So graph y equals the square root of x plus 3 and y equals square root of x minus 2. So arrow square root of x plus 3, so it'd be x minus 8, so h would be negative 3. So we'd rotate to the left, translate to the left 3 units. And then on the second one, x minus 2, we translate it 2 units to the right. Again, one way to think about it is what's going to make the radical 0? What's going to make that 0? That's one way to always think about it. So the graph is, we've already done it, shifted 3 units to the left. The graph of square root of x minus 2 is the same graph, shifted 2 units to the right. The range of both functions are a set of non-negative numbers, but their domains differ. Their domains differ. All right, so graph square root of x minus 1 and the square root of x plus 4. Bam, there's a graph for you. So let's work on the first one. Y equals the square root of x minus 1. So that's going to be our base graph, but it's going to be translated 1 unit to the right. Okay? And if you have to think about it, when x equals 2, y would be 1. When x equals 5, y would equal 2. And there's the first one. So the second one is y equals, let's just hold on, the domain would be x has to be greater than or equal to 1. The range would be y is greater than or equal to 0. Because remember, we cannot have a negative radicand and we cannot have a negative number. So let's look at the second one. Y equals the square root of x plus 4. So this is going to shift us or translate it 4 units to the left. Okay? So the domain would be x has to be greater than or equal to negative 4. The range is the same range. Y has got to be greater than or equal to 0. Alright? So when x equals 0, y is 2. Alright. And when x equals negative 3, y is 1. So there, we can graph the whole thing again. There you go. You can still plot points. You know, choose easy ones to do with the radical signs. That's what I would do. Okay? So look it over. Do you see how I got the domain? I made the radicand equal to 0. That's going to be the domain. It's got to be greater or equal to that number. And the range in this case is always going to be y is greater than or equal to 0. Alright, the graph of y equals a squared of x is a vertical stretch or compression of the graph of y equals square root of x by a factor of a. If a is negative or less than 0, the graph is reflected across the x-axis. So graph the square root of x, that's the blue one. Nice and easy. Graph 1/2 the square root of x, and again, that one's going to be flatter. And then graph 2 square root of x, and that one's going to go up faster. For each value of y, 2 square root of x is 4 times the corresponding value of 0.5 square root of x. The domain and range of all 3 functions are set of non-negative numbers. So, next example. Find the graph of negative square root of x, and then y equals negative 2 square root of x. And voila, there is our graph again. How magical is that? So let's work the first one. Y equals the negative square root of x. Well, this is the base graph. So we're going to do it in red. So when x equals 0, y is 0. When x equals 1, y equals negative 1. When x equals 4, y equals negative 2. That's good enough for us to graph right there. Alright, so now let's look in purple. Y equals negative 2 square root of x. Okay, x equals 0, y equals 0. When x equals 1, y equals negative 2. When x equals 4, y equals negative 4. Alright, and if you wanted to do 9, it would be negative 6. So you can graph that one. And it goes 2 times. And again, when I have a radical sign, when I have a radicand, I'm thinking of using things that are perfect squares to get it to 0, 4, 9, and 16 if needed. Okay? Going on to the next example. In general, the graph of y equals a times the square root of x minus h plus k is nothing more than a translation of h units horizontally. So h is just like it's always been, left and right. Our k values up and down. And our a is going to kind of either compress or constrict, okay, our graph. So here we go, graphing a square root function. So it says graph -2 times the square root of x plus 1 minus 3. So this is going to be the parent function of y equals -2 square root of x. So there's our base function, there's our parent function. And so now it's just going to translate it 3 units down and 1 unit to the left. That's going to take me to the left 1, that's going to take me down 3. And it's going to be the corresponding graph. It's going to be the exact same coordinate values. Okay? So let's look. So graph y equals 1/4 x minus 2 minus 4. So the parent function is y equals 1/4 the square root of x. We're going to translate it 2 units to the right and 4 units down. So let's graph the parent function first. We'll do that in purple. So 0, 0 stays. Okay, so when x is 1, y would be 1/4. When x is 4, y would be 1/2. When x is 9, be 1/3. And we'd get all the way to 16 before we cross 1. So it's going to look like this. All right, but we're going to do the exact same graph, but we're going to shift it 2 units to the right and 4 units down. It's going to look the same. Just translated. Okay. Again, how did I get my coordinate points? I made x in my mind equal to 0, 1, 4, 9, and 16. All right, going on to the next example. So we have a function 0.4 to the cube root of x models the height, the h of meters of a female giraffe that has a mass of x kilograms. All right, we're not going to do this part. We're not going to graph with a graphing calculator. We're better than that. All right, but however, we can still solve for the equation. So the height of the giraffe is 2.5 meters. So we can say 2.5 equals 0.4 times the cube root of x. So divide everything by 0.4. So we get 2.5 over 0.4 equals the cube root of x. So we're going to cube each side. So x is going to equal 2.5 over 0.4 cubed. Let's go ahead and get our handy dandy calculator out. All right, let's check her out. So let's put some parentheses up. 2.5 divided by 0.4 cubed. 244.14. So x is going to be 244.14 kilograms. Okay, easy enough for us. We know how to do that. Okay, going on. Next example. The pattern for graphing the square root functions applies to other radicals as well. For example, the graph of a to the cube root of x minus h plus k is still a translation of h units horizontally, k units vertically, of the parent function of y equals a to the cube root of x. So example, graph y equals 2 times the cube root of x minus x plus 3 minus 1. So the graph is really the parent function of y equals 2 times the cube root of x. So we can plot some points. We did that with this one. And now all we got to do is translate it 1 unit down and 3 units to the left. So we translate that 1 unit down, 3 units to the left, and we just match it. Okay, not too difficult. Let's look at the example. So I got y equals 3 minus the cube root of x plus 1. So this is going to translate 3 units up, 1 unit to the left, and the parent function is y equals the negative cube root of x. So let's graph the y equals the negative cube root of x.